Alright, so let's continue our discussion about understanding limits graphically and numerically. So we are now on example 2, and let's think about this. We think of the function as a highway, and the point at 2 comma negative 1 could be considered the end of the road. So if we go back to the graph that we were looking at earlier, and 2 comma negative 1, right? If we consider that point, that could be the end of the road. Right? So if we come back, while the point at negative 1, 2 is more like a pothole. So negative 1, 2, big old hole, consider that like a pothole. Right? So while the point at negative 1, 2 is more like a pothole, how would you describe the points located at 2 comma 1? So if we come back over here, 2 comma 1, big old hole, right? You can almost consider, but it has an ending, so you can consider it like this. It could be more or less a dead end without a barrier, because it continuously goes, but it's a big old gap, like Grand Canyon. Okay, so we look at 4 comma 3. Okay, so here's 4 comma 3. Looking at it, almost looks like a bump in the road, because it kind of goes up and then comes down. So it's like a bump. All right. So hopefully this analogy gives you a visual reference for understanding limits from a graphical approach. So let's get a little more formal with our definition now. When finding limits, ask yourself, what is happening to y as x gets close to a certain number? You are finding the y value for which the function is approaching as x approaches c. Right? So here we go. So the limit existence theorem goes as follows. The limit of f of x as x approaches some constant number exists if and only if the limit of f of x as x approaches the constant number from the left equals the limit of f of x as x approaches the constant number from the right. And that would be your big L, where the big L is a real number. Okay? So verbally, this just again says the limit as x approaches c on f of x will exist if and only if the limit as x approaches c from the left is equal to the limit as x approaches c from the right. All right, so let's move on to the next example. Limits can fail to exist in 3 situations. In case 1, we see that a limit as f of x approaches negative 1. So justify why the limit does not exist at x equals negative 1 for f of x at x plus 1 over x plus 1. So all you got to do is what we're going to do is we're going to find the limit as x approaches negative 1. Oh, that's bad, negative 1. Negative 1 from the right side. Right? And we see on the right side, it's easy enough to know it's approaching 1. Alright, so let's now look at the limit of f of x as x approaches negative 1 from the left side. So again, if we look at that one, it's negative 1. So since limits of f of x as x approaches -1 from the right does not equal the limits of f of x as x approaches -1 from the right. Also, we can also look at this and kind of distinguish between this. This case is called limits differ on left and right. Right? So that's pretty straightforward. Limits differ on left and right. In case 2, it says justify why the limit does not exist at x equals 0 of f of x of sine of 1 over x. So by inspection, we're going to look at x equals 0.1. And we see that the limits of f of x as x approaches 0 from the right side, so here's 0.1-ish, we can see from the right side, it looks like it might be less than 0. While at x equals negative 0.1, that's a 0.1, so make that better. All right. We see that the limit of f of x as x approaches 0 from the left is greater than 0. So therefore, that right there means therefore the limit does not exist. Okay. Now this case is called oscillating behavior. It's jumping from positive to negative, positive to negative, positive to negative, positive to negative, and not actually just flowing, just jumping up and down at a really fast heart rate. Right, so let's look at the third case. Case 3 says justify why the limit does not exist at x equals 2. Right, so we're going to look at this. So the limit of f of x as x approaches 2 from the right, side, it's going towards infinity. And the limits of f of x as x approaches 2 to the left, you see it's also going towards infinity. So therefore, the limit of f of x as x approaches 2 must be infinity. So by definition, infinity is not a real number. It's kind of more like a symbol. Infinity is more of a behavior of f of x. So when we get an answer that it's infinity or negative infinity, because they both could have been down, this is just called an unbounded behavior. Alrighty, we get done with this one. I'll have one more video for you.